Hello everybody. If you're a fan of my channel, you've seen me use my sharpening station and other ways to sharpen plane irons, chisels, and other things. And one of the things I always emphasize is to make sure when you're sharpening a plane iron that it remains square. But I'm not a machinist, and I've often wondered just how square does it have to be. And while we're at it, how perfect does this edge have to be? And I'm not talking about sharp, but I'm talking, straight and true. Because when you're using a hand plane, you're obviously trying to get very, very fine shavings. And again, we're talking about wood here. Probably a lot of ways to get a feel for this, and I'm probably going to do it in one of the more complicated ways. So stay tuned. And for those of you not terribly familiar with how the hand plane works, I'll use this number 5 for illustrative purposes. So there's not a lot of precision here, but it should get us in the ballpark. If I take this off, you can see that the wheel on the lateral adjusting lever is pivoting down, about a ½ inch above the depth adjustment tab. So you put the iron on and that puts the wheel somewhere up around here, which puts it about right up here in the knuckle area of the lever cap. The lever cap pushes down here, the very edge of the iron, so I think it's fair to say what happens is when you move the lateral adjusting lever, it pivots on a point down here. If I move the lateral adjusting lever to the right side of the plane itself, or the left as you're looking at it, it's kicking the iron to the left of the plane itself. And what that is doing, to illustrate here, is it's tipping it this way, exaggerating for effect. It's pushing the left side of the iron deeper than it was cutting before. And conversely, if you move the lateral adjustment lever all the way on the other side, it tips the iron the other way. So to illustrate this point, this iron here, and it's pivoting somewhere down here, and you're tipping it this way and tipping it this way. And the question is, how much do these edges move? So what we need to do is determine how many degrees it can tip left and tip right, and then use that information to figure out how much the left edge will move up and down in the corresponding right edge. So I didn't feel like taking apart one of my number 4s, but I have a frog here to an old number 3. Which has been the topic of a video or two. And if we move the lateral adjuster all the way down, and I very carefully line up this ruler with that edge, you can see we're around 3 7/8 in total length. And if I move the lateral adjuster all the way up, and I try to measure this distance, get somewhere around 5 or 6/16. So just to review a little high school trigonometry, and this is a very cursory explanation. There's tons of other information out there. Let's say you have some random triangle. You have to have a right angle down here, and there's 3 components to the triangle. This is known as the hypotenuse. And if the angle we care about is here, then there's an opposite and there's an adjacent. And similarly, if we draw the exact same triangle, or close to it, and this is the angle we care about, then for this guy again, we have the hypotenuse. But in this case, this is the opposite and this is the adjacent. So you just have to keep these relationships in mind. Have to have a right angle. You got to figure out which angle you care about. For either of these triangles, it's simple. The sine of the angle equals the opposite divided by the hypotenuse. The cosine, the angle, is the adjacent over the hypotenuse, and the tangent of the angle is the sine over the cosine, which equals the opposite over the adjacent. And this is true for all right triangles, and this is simply a ratio. So if you have a right triangle with this exact angle, it doesn't matter how big the triangle is, this dimension will get bigger, exactly the same as that one, exactly the same as that one. So I'll leave the frog here for a reference, but the length of the triangle is 3 7/8, which brings it somewhere around here. Overshot it a little bit. And that is 3.875 inches. The height we determined is 3/8 of an inch, and again I'm going to exaggerate a little bit for effect. And that's 0.375 inches. And the right angle is down here. And to fill out the triangle, very small angle, looks something like this. And what we're interested in knowing is this little tiny angle in here. That's the question mark. So the tangent of this mystery angle is the ratio of 0.375 over 3.875. Okay, so the tangent to the -1 of this ratio, 0.375 divided by 3.875, it's about 0.1 .096 to be a little more accurate, equals question mark. So we do second tangent, and that's 5.52 degrees. And that's 5.5 degrees. And just for giggles, if I take .096, instead of doing the inverse tangent, we do the inverse sine, we get pretty much the same answer. So to illustrate that with this guy here, that means it tips this way and this way. And since that first calculation was the full range of motion for the lateral adjuster, I think it's fair to assume that it goes 2 1/4 degrees to the right and 2 1/4 degrees to the left. And this particular iron is 2 inches wide for number 4. So to do that diagram, we'd have a triangle something like yo. So that's representing this guy here tipping down 2 1/4 degrees. So this angle in here, 2 1/4 degrees. So again, that's 2 1/4. This dimension here is 1 inch. And what we're interested in here is this length here. So again, the tangent is the opposite over the adjacent, and the adjacent is 1 inch. So the tangent, 2 1/4 degrees, equals the length we're looking for over, by coincidence, 1 inch. So if we pull that over here, punch in 2 1/4 degrees, and just find the tangent, it's 39 thousandths. Let's call it 40 for convenience. So the thing we're looking for is about 40 thousandths of an inch. But that's not the end of the story. So let's pretend this piece of paper represents the body of the plane, and this square represents the frog, and this ruler represents plane iron. As you operate the depth adjustment knob, this plunges the iron down below the mouth of the plane to give you a depth of cut. So let's say we are there and we plunge it 1 inch beyond the sole of the plane, and I'll put this ruler here for illustrative purposes. That 1 inch extension doesn't give you a 1 inch depth of cut. It gives you something closer to 3/4 of an inch. It's actually 7/10 of an inch, and that comes about because the frog is at an angle and we have to use trigonometry once again. Give you my artist rendition, and if this is 45 and this is 90, then this is 45. Not a great drawing, but you get the idea. And if this unit is 1 unit, then these two sides are .707, about 7/10. So when the iron is rotated the full amount by the lateral adjuster, this edge we already determined goes down by about 40 thousandths of an inch. Because it's on the frog at the 45-degree angle, you have to derate that by 7/10. So instead of the edge of the iron plunging down 40 thousandths, you'd have to derate that by 70%, so it would only be about 28 thousandths. And a larger iron, larger plane, greater rotation would give you a greater depth, and a smaller plane with a smaller iron will give you a little less. And I don't have a different triangle, but I do have this block cut to 30 degrees. And let's just say you have a low angle plane, like a low angle block plane. To illustrate the same thing, if this is the iron and it goes at a 30-degree angle down the mouth of the plane, and this amount is even shallower. Instead of 7/10 of an inch, you can see it's closer to a 1/2 inch. In fact, at 30 degrees it actually would be a 1/2 inch. And I'll leave that trigonometry up to you. Well, so that's a good mental exercise, and another way to do it, although not as fun, would be to just try to measure it directly. Here I have my Bailey number 5 in the vise with a white background, and here we have the blade very much projected. If I try to measure it carefully, we're getting around 40 thousandths, maybe a little more on this side, maybe 50 on this side here. And if we tip the blade all the way in one direction, we try to measure it, the 40 goes up to, looks like a little north of 60, hard to tell, and down here we're probably around 20. So we extended that end by 20 thousandths, and if we tip it all the way the other way, this side is now down around 20, and this side is up around 60. So it looks as though you've got a good 20 thousandths to the left and 20 thousandths to the right. So we were calculating something on the order of 28 thousandths. We measured something on the order of 20 thousandths. Yeah, that's close enough for me. So, and you have to remember that this 20 thousandths of play is mitigated by the fact that the frog is at an angle. You have to multiply the number. Instead of, remember, we were multiplying it by 0.7 when we went from the iron to the projection. Now we're going from the projection back to the iron, so you multiply by 1.4. So 20 thousandths in play at the plane means you have to be able to sharpen it to within, say, 28 thousandths on either side, which I think is pretty easy to do for the common person with common shop tools. So there you have it, in case you were wondering. And that's all I got for this video. Hope you got something out of it. Please let me know what you think. And if you enjoyed it, like, subscribe, leave a comment. Thanks.